Um, Essentially, yeah, as you guys know, you've got the quiz 2 on Saturday. The stuff which is going to be on quiz 2 will be frames, beams, and trusses, essentially, right? The stuff that Wade talked about, in this week's lectures regarding friction and fluid statics will be in week 10. That quiz, okay? Sorry, and I forgot to mention section properties. Section properties is also possibly going to be in your test this Saturday, all right? So those are the things you want to look out for. However, there's not many weeks left for the rest of this term, right? So I want to get you guys started on dynamics. I'll try to go relatively slow where possible, but there's quite a bit of content to cover. The reason why I want to go to dynamics now is because if we don't start dynamics this week, I'm afraid it will be more difficult for you to do your assignment. So I would like to just jump right into it. The topics that Way's covering right now in the lectures, fluid, like hydrostatics and friction, are actually very, very simple. So I'll do those in week 10. And week 10 will also be an opportunity for you guys to just ask any other questions that you have, I guess, and we can like consolidate it. So that'll be a little bit of a recap as well in week 10. So that's kind of the plan going forward. So today I just want to talk about dynamics. So, okay. So essentially where we are at the moment, and I have this in the wrong spot, is we've moved over to the dynamics part of the course. And we're going to start with talking about particles before moving on to rigid bodies. As I mentioned before, particles are zero-dimensional, okay? Whereas rigid bodies you're going to start to treat as one-dimensional or two-dimensional objects. Three-dimensional objects won't be in this course. But I'll give you an example, like a pool table ball, right? We can treat as a zero-dimensional object where we just have it as a mass and the position of it is like the middle of the pool ball, right? We don't, depending on like the type of analysis we're doing, we can just treat it as a mass with no specific dimensions, okay, in space. Okay, so that would be like an example of particles. So that's what we're going to deal with in today's workshop. And we're going to be talking about one-dimensional and two-dimensional kinematics. So kinematics, put simply, is just talking about the motion of objects in terms of its displacement, velocity, and acceleration. So I guess this is like building off of your understanding of physics from year 11 and 12. And I believe you've all done physics 1A. It's kind of just building off of that. So all of this stuff should feel relatively familiar, I want to say. We're just going to get you familiarized with a couple of terms, okay? So again, we're in the realm of talking about different types of motion. First, I'm going to run through rectilinear motion. So rectilinear just means, well, in terms of 1D motion, rectilinear just means in a straight line. Okay, but once we talk about 2D motion, rectilinear is going to be talking about movement in 2 dimensions, except the important thing is that we're going off of a coordinate system that is like XY coordinates, for example, right? Or normal tangential coordinates, for example. So that's rectilinear. The reason why we say rectilinear is because there's a different type of movement or coordinate system that we can consider as well, called the curvilinear coordinate system. And this is where you're talking about things following a curved path or a circular path. You'll be talking about it in terms of like a radial distance and a angle, for example. Or yeah, like if you're swinging say you're swinging a ball around on a string, you've got the normal direction, which is if I'm swinging the ball around on a string, that would be the direction of the string, and the tangential direction's the direction that the ball wants to go, okay, at that specific point in time. And then we'll also be talking about relative motion. So say that's object A and this is object B. It's like, what's the movement of object A relative to B or B relative to A? I'll explain how that works. And then week 8 onwards, we'll be talking about equation of motion, which is F equals ma, and we'll be talking about energy conservation, so work energy methods. And we'll also be talking about impulse momentum. So there's quite a bit packed into this part of the course, which is why I want to start with the dynamics portion this week. Otherwise, it's going to be way too rushed and you're not going to learn it properly. Do you guys have any questions about any of that? Nope. Okay. I was just checking if I was recording, which I am, which is good. Let's check if the audio is working. That would be, okay. That's very good. Okay, so let's break down the motion quantities a bit more. Displacement, velocity, acceleration. So the way that these three quantities are related to each other is through time. Okay, so time is the derivative. So for example, if we have displacement and we go and we derive it with respect to time, we get velocity, and if we derive that with respect to time, we get acceleration. And going the other way, we can integrate, right, with respect to time. So if we integrate acceleration, we get velocity. If we integrate velocity, we get displacement. So this will be how I'm kind of notating these quantities. So displacement will be s with a hat, velocity will be v with a hat, and acceleration will be a with a hat. Okay. So okay. I'm going to go through two methods for solving these motion quantities, right? So this is the kinematics kind of methods, right, that we're going to go through. And we're going to start with one-dimensional motion, okay? So we're just dealing with something moving in a straight line, right? It can move backwards and forth. Like, for example, if I throw a ball up, right, and then it's following the path of gravity, so it's going up and then back down, that's still one-dimensional motion, rectilinear motion. This is going up and then back down in that same path, okay? Okay, so the first method that I'm going to show you is the initial conditions method, which is probably, if I was to guess, what you guys learned in Physics 1A and or high school. It's where you have indefinite integrals and you plug in kind of additional information to figure out the integration constants, right? It's more intuitive, I would say, but it starts to break down with more complicated questions. So the second method, which I'll show you in the second question, is the separable ODE method. Okay, so you might not have come across this before. ODE stands for ordinary differential equation, but it's actually quite simple. It's just less intuitive why we do it, but it will give you the correct answer for more complicated functions. So I would say this is the preferred method in a lot of ways. There's a bunch of steps here, but I won't really run through them now because it just makes more sense to see in the question. Okay, so this will be what so this separable ODE method is what I'm going to run through for question 2. But before we move on to that, I'm going to show you question 1. All right. Let me get the question up. Okay, so let's read the question. It says a particle starts from s equals 0, which is displacement of 0, and travels along a straight line with a velocity following this function. Okay, so what they've provided you on the right is a graph, which is a parabola, which maps out the velocity. So this parabola function follows this formula, basically, right? And on the x-axis, we have time, okay? So, yeah, t is in seconds. Construct the displacement versus time graph and the acceleration versus time graph between the time interval of 0 to 4 seconds. So what you see in this graph is between 0 to 5 seconds, but yeah, we just constructed between 0 to 4 seconds, basically, for the displacement versus time and acceleration versus time graph. Okay, so the first thing we do, knowing that if we're starting here, if we're starting at velocity, right, and we want to get to displacement and acceleration, to get to displacement, we're going to need to integrate, and to get to acceleration, we need to differentiate, okay? So you kind of have to understand that hierarchy. So let's do acceleration first. So we'll differentiate. It's a polynomial function, so relatively straightforward. Just a little, here's how I always like to warm up with polynomial integration and derivation if I haven't done it in a while. Just remember that if you have x squared, right, when you differentiate it becomes 2x, right? So just remember what you're doing, okay? You're multiplying the power up the front, and then you're bringing down the power by 1, right, in that order. So that's for differentiating, right? And you go the other way around for integrating, except you have to add the plus c for indefinite integral. Okay, so what we do is, because we have a sum of terms, right, we go through these terms one by one, and we just, apply our differentiating, okay? I actually really hate explaining algebra. Not algebra. I really hate explaining calculus out loud while trying to teach a class, because it's it trips me up a lot. Okay, sorry. Okay, so t squared becomes 2t, okay? And then we look at the next term, so we go minus 4t becomes 4, and then 3, since it has no t term, just becomes nothing. It just gets vaporized, okay? So this is basically going to be our acceleration function. Displacement, remember we're taking this and we're going the other way, right? So we're integrating now, right? So t squared becomes t cubed, and then we divide by that power, okay? And then the next one is, here's what I'm going to trip up. Okay, 4t, negative 4t becomes 2t squared, okay? And then positive 3 becomes 3t, and you have to remember to add the integration term, the constant, okay? So what we need to do is, like in the question, you're usually given the integration constants because they're initial conditions, right? So we're told that at time is equal to 0, right? Okay, when the particle starts, we know that the displacement is 0, right? So what that's trying to say is when time is 0, displacement 0, and so c is equal to 0, because this is so the left hand side will be 0, the right hand side will be 0, and so therefore c has to be 0. Okay, so this becomes 0. So essentially our displacement function is just this. Okay, cool. So yeah, that's calculus basically, right? Okay, so next we graph it, because we're asked to graph the acceleration versus time and the displacement versus time. So for acceleration, this is the function we have to graph, and it's a straight line function, right? And negative 4 is our y-intercept, right? So if you think of a straight line function, right, y is equal to mx plus b, right? Negative 4 is that b term, so that's down here, and we've got a gradient of 2, right? So that gradient is going to be 2. And what we might want to do is we might want to find the other values of interest on this graph. So for example, the t-intercept, as well as whatever acceleration is at t is equal to 4. So using our graphing methods, what we would do is basically we get the acceleration function, this one, and we set the left-hand side to 0, okay? And then we write 2t minus 4. If we solve for t, we get 2 seconds. So what that's trying to say is we've plugged in acceleration is equal to 0, which is this straight line, and we're trying to work out this value on our horizontal axis, which is going to be t is equal to 2 seconds, right? The other one is going the other way, so we're going to plug in that time is equal to 4, which is here, and we want to find where this hits horizontally, I guess. So we have our function again, so 2t minus 4. We get 2, we plug in t is equal to 4, so 2 times 4 minus 4 gives us 4 meters per second squared, okay? So yeah, that's graphing. Okay, sorry, this is really basic. I'm just going to go through everything the first time very slowly, and then if you've seen it before, you can assume that I'm just going to do it a lot quicker. Okay, so next we're going to graph parabola, basically. And I'd say the easiest way to find out these t-intercepts of the parabola, t-axis, right? We know that by looking at it, but the way that I solve it for some reason is by getting the displacement function, right, and setting where displacement is 0, right? I think what I'm trying to do is say where the peaks, where this curve is flat, right, is also where here and here are. Okay, so basically what I do is I get this, I get the function and I take the t factor out, and then I also take I multiply all the terms by 3 inside here, and then take 3 out as well. So I factor out 3. So it goes 3t. So then it goes t squared minus 6t plus 9. Okay. Okay. Apologies. Okay. So now I've got these terms here, and it's still all equal to 0. What I do is, this is a perfect square, right? So I go 0, 3t, t minus 3 squared, okay? So that becomes all that. And the idea is that at t is equal to 0, 3. Okay, let's see what I'm confused. Okay, so basically that's these points. It's where the t-intercept is being hit for s. Okay, I think I see what's going on. For this one, okay, here's how you actually solve this one. Okay, so if you set it equal to 0, right, that's this line. Okay, and then if I solve for t, right, it's basically t minus 1 and t minus 3. Okay, there we go. So that's saying that at t is equal to 1 and t is equal to 3, right, that is our x-intercepts, our t-intercepts rather. Okay, so that's that one, which is separate to this one, which is what I was misreading. Sorry. Okay, so t is equal to 0 and t is equal to 3 seconds, right? These ones are the intercepts for the displacement first time graph, okay? So that's where I got mixed up. So other important values which I might be interested in is finding what s is. So s, remember, it's the vertical axis, right, on the displacement time graph. So I might want to find what s is at time is equal to 1, time is equal to 3, and time is equal to 4, okay? So, like, in order to graph this line, basically, right, this cubic. So if I sub in t is equal to 1 here, for example, I'll get this, and that would give me 1.33 meters. And if I sub in 3 instead for all of these values, then I would get this. And if you compute that, it gives you 0. And for t is equal to 4, so if I do 4 instead for all of these, okay, then I get all this. And if you compute that, that's 1.33, okay? All right. Fantastic, we made it to the end. Okay, so that's question 1. All right. So question 2, right? Question 2, we're gonna do using the separable ODE method, okay? So for this particular question, it's about this dude throwing a ball up and like from a building, which is 20 meters off the ground, like his initial position is 20 meters off the ground. He throws it at 10 meters per second up, and we know the acceleration due to gravity. So what all these things mean is saying that at s is equal to 0, we start at 20 meters off the ground. Not when s is equal to 0. At time is equal to 0, we're at 20 meters off the ground. At time is equal to 0, our velocity is 10 meters per second. That's our initial velocity. And the entire time, acceleration due to gravity is negative 9.81 meters per second squared. Okay. So, what the question is asking from us is, what is the maximum height the ball reaches? What is the speed of the ball at this moment, and when does it occur? That's part one. So it's asking basically what is the height at the apex of the throw. For part B, when does the ball hit the ground? Right. That's saying when does the ball end up reaching s is equal to 0. Okay. And then lastly, draw the displacement time and velocity time graphs. Okay, so we start off with acceleration, right, which we know is acceleration due to gravity. Here's how the separable ODE method works, all right? So the first thing we do is we write acceleration as the derivative of velocity with respect to time. That's what we're going to do first. All right, let's just leave it as equal to negative 9.81. All right, next you have to pretend that dv and dt, let's do it in a different color, are like a fraction. And then you have to treat it as if you multiply both sides by the denominator of that fraction. Okay, so we're going to move dt onto the right-hand side. Okay, so it'll be dv and then dt, okay? And then we have to integrate it. So we have to separate it and integrate it, okay? So when I say integrate, we're doing this. Sorry, 9.81 is outside the integral because it's a constant, like so. All right, and now for the integral bounds, right? The initial, so we've got where the integral starts and then where it like ends, right? For the initial part, we're gonna use the information from the question. So where velocity starts, right, is 10 meters per second, okay? So we do 10, and where it finishes, quote unquote, is gonna be v, okay? So v is gonna be like an algebraic variable that we're gonna basically put there so that we get a function, right? And then on the right-hand side, we're going to do a similar thing. So time is going to start at 0, and then it's going to finish at t. Okay. All right. So now we solve the left-hand side and the right-hand side separately. Okay. So if we do this as a definite integral now on the left-hand side, we get v. Okay. So imagine there is like an imaginary 1 there. V integrates to v. Sorry, 1 with respect to v integrates to v, right? And then here are our integral bounds. 9.81 is out the front. Similar thing happens for t, right? So if you imagine a 1 there, if you do the integral of that with respect to time, you get t. Okay, and then those are the integral bounds. Okay, and now we evaluate our integral bounds. So we go v, we sub in v into v, and then subtract the initial integral value. So we sub that in for v. So that looks like that. This is negative 9.81. And then it goes t minus 0, and then you can ignore the 0 part. So this is our function so far, and what we do is we have to isolate v, all right, and this is going to give us our function. So if I move 10 to the other side like so, this gives us our function. So now this is, so we went from acceleration, and using the separable ODE method, we got to v basically, right? Okay. So now we know that velocity is the derivative. Sorry. We know that the derivative of, sorry, okay, velocity is the derivative of Okay, basically v is equal to ds over dt, right? That's what I'm trying to say. So we just equate that, and then we do the same thing. So we separate and integrate. So let's say, I'm gonna use these colors. Okay, so dt moves on to the right, ds stays here, and we chuck an integral onto both sides, right? Like here and here, and yeah, and then for our integral bounds, we do the initial condition, right? So the initial condition for displacement was 20 meters, okay? And then our final condition is the function that we're solving for. And on the right-hand side, initial condition is going to be time starts at 0, and it's going to finish, quote unquote, at t. Okay, and when we compute that, we get this, right? So we've solved that definite integral and get this, and now we just move 20 onto the right-hand side. Okay, so this is now our function for displacement. Okay, so going back to the question, what is the maximum height the ball reaches, and what is the speed of the ball? Oh, sorry. So at the apex of the throw, what is the speed of the ball? So the idea is that when the ball reaches the apex of the throw, it's not moving up or down, so it has a velocity of 0. And so knowing that information, what's the maximum displacement that's reached? Okay, so how far does it go relative to the ground? Okay, so v is equal to 0 at the apex of the throw, and this is the rest of the function that we found for velocity, right? Okay, so since 0 is equal to all this, right, we can just solve for t, right? So let's say I move this to the left-hand side and then divide both sides by 9.81. I would get t is equal to 1.0194 seconds. So that's the time until the apex. So once I've solved for that, right, how long it takes to get to the apex of the throw, I can plug that into our displacement function, right? So it's saying that after 1.0194 seconds has passed, what displacement am I at? And that's just a matter of basically getting the displacement function, and then every time you see t, you plug in 1.0194 seconds, okay? And that gives you the maximum height. Okay, so the maximum height is 25.097 meters, okay? So that's the apex of the throw. All right, the next part of the question is saying, when does the ball hit the ground? So the part that we know from the wording of the question is basically, I clear all this, right? We started up here at plus 20 meters, it goes up and then back down. So what time are we at when the ball gets to s is equal to 0, which means hits the ground, okay? So we have our function, and now we have to solve for, we have to solve it quadratically, basically, and you'll find that if you do the quadratic equation, you'll get time is equal to negative 1.24 seconds, or 3.28 seconds. So obviously you can't have a negative time, and so yeah, we're going to be in, like, this will be the time that the ball, how long it takes before the ball hits the ground, okay? All right, any questions about the ODE, separable ODE method? Okay, what I'm going to, oh, and there's just the graphs left to show you, so I'll leave that on the screen for now. Before I move on to the second part of the workshop, the 2D coordinate systems, I'm going to come around and, because I know you're all kind of studying for the quiz, right? Just feel free to ask questions about anything. All right, basically, in 1300, you're going to see different 2D coordinate systems, and when I'm talking about 2D coordinate system, I'm talking about something like the XY plane, right? So obviously no third dimension, no like Z direction or whatever. And you'll also see NT being the normal tangential plane. So normal tangential plane is useful for when you have motion on inclined ground. So you've seen stuff like that. Oh, actually, I might go through in order. So XY motion, you'll see this used when you have motion on flat ground, like this, for example. And you have someone like pulling it or whatever. Projectile motion, I mean, we've gone over a one-dimensional projectile motion question, essentially. It's just that vertical throw of the ball off of the building, right? But in 2D, you'll see it goes like that. And we're tracking the ball's motion in those 2 dimensions, the y dimension being the direction of gravity. And relative motion, yeah, you have like plane flying due north or something, and you have another plane flying like due east and all that stuff. So it's relative motion. Relative motion can, be in the context of things other than, planes, boats, and like cardinal directions, but that's generally how it's presented. Yeah, and then for the NT plane, it helps when you're solving questions which are to do with motion on flat ground. When the ground's inclined, basically, looks like this. Right. Generally, it helps to solve everything in terms of this normal tangential plane, because the first step in solving these kinds of questions, we'll get into more detail about this next week, is, like the direction of the weight, right? That's mg, which is pointing towards the earth. And then we have, sometimes you have friction, right? Sometimes you have the direction that's being pulled, or it could even be inclined like that. And normal force is always perpendicular to the plane, right? So usually you go mg to n to friction slash, to friction, let's just say, right? So yeah, it helps with the unknowns, which are generally like n and f, to break things up in terms of taking the sum of the forces with respect to the normal and tangential directions. Sorry, that was a mess. And curvilinear motion. Let's see if I have a drawing for it. So you're tracking a particle's motion, right? You're going to have acceleration in the tangential direction, tangential to the circle, and normal to the circle will be our centripetal acceleration, right? I want to quickly say, this is a realization I made just now in the break. The motion on inclined ground and flat ground, generally this is to do with Newton's second law, which is like, sum of the forces, that kind of stuff. Every time I look up the definition of kinematics and kinetics, I get confused, but I'm pretty sure that's kinetics. I'm pretty sure whenever we deal with the forces stuff, right, it's actually next week's topic, right? What we really care about for, kinematics are like when we're just tracking the motion, like without respect to the forces, right? But I'm just giving examples ahead of time, I guess, on like coordinate systems, right? So these are the kind of coordinate systems you'll see next week as well, right? Okay. Another one you'll see in the mining school or mech school is polar motion. Okay, long story short, you don't need to know it, but sometimes you have like a satellite that's tracking a rocket's motion, and it helps to track it in terms of a radial direction and angular direction. And also helps, if you're programming like a robotic arm that has that's spinning around and it's oscillating its, hand part like that. That's like sinusoidal motion. Yeah, that's polar motion, but we don't care about it in this course, basically, right? Sorry, in the civil school for this course, right? Okay, does anyone have any questions to do with those concepts? Okay. So yeah, again, I've included this, but this is technically a part of next week. It's kind of weird, right? So the way they generally teach dynamics or particle dynamics in this course is they like to teach you about Newton's second law for very basic cases first. So, you're taking some of the forces for, incline and flat ground and that kind of stuff, and you have friction involved and whatever. But that's technically kinetics, right? But kinetics, there's more to it than just Newton's second law. Like kinetics, we're going to deal with work energy methods and impulse momentum methods, right? And for kinematics, which is what we're kind of going over today, we have our 1D and our 2D stuff, right? So 2D is what we're going to go over soon. 1D was our straight line motion, etc. I've sort of taught it like this, where we're going to go over 1D and 2D I read the same thing twice. Kinematics. I'm going to teach it like 1D, 2D, and then go back to this stuff. But, some textbooks, some courses, they like to teach it this one first, and then you move on to kinematics. You jump back to kinetics and do like those work energy methods and impulse momentum methods. Do you know what I mean? So it's like, that's why I think the words kinetics and kinematics always get mixed up, because the order in which it's taught is usually kind of just back and forth. You know what I mean? Anyway. So yeah, this is basically part of kinetics, so we'll end this one as well. So we'll talk about that next week. Projectile motion, right? Here are the formulas I would use for projectile motion. It's just an extension of what we kind of did in question 2 there. Essentially, these are those like hidden values which are implied. It's that the vertical acceleration is due to gravity, and the horizontal acceleration, we don't account for like air resistance and wind and stuff like that usually. So we just say that the horizontal acceleration is 0, right? So it doesn't, it just stays a constant speed when you fire a ball out of a cannon or whatever, right? Okay, here's something which I like to keep as like a kind of rule of thumb. The function is your initial plus your change component, right? So this is like, okay. Basically, your function for velocity is going to be your initial velocity plus the change in velocity, right? Acceleration is like dv dt multiplied by time, right? So I just call it acceleration multiplied by time, right? So in the horizontal direction, that's 0. So essentially our horizontal velocity is just equal to our initial velocity. That's just set. So as you fire a cannon, like a cannonball out of a cannon, that speed just stays as its horizontal speed the entire time, right? And when you integrate that, it's just multiplied by t, right? Because we've integrated with respect to time. So we've done a definite integral where the c is cancelled out essentially, right? Because we're starting at t is equal to 0 for my simplified formula here. And for the vertical velocity, right? We take the vertical component of that speed, but now we have to account for gravity changing it, over time, right? So yeah, and then when we integrate that, we have to also account for that component, right? And so, yeah, that just becomes a higher order essentially, right? Okay, hopefully that makes sense. These are general like formulas which will keep coming back when we're doing projectile motion questions essentially. But it's all derived from that idea of function is equal to initial and the change component, like the initial component, the change component. Okay. Oh, and sorry, usually the initial component, right, these ones, is based on like, your cannon or whatever, for example, we're firing, usually given this angle, or if you're not given this angle, you have to solve this angle. And then you can break it up using your force components that we've kind of talked about in week 1, right? So the x component of, it's not a force component, it would be more like a velocity component, velocity being like a diagonal arrow, like a diagonal vector, and you can split it into the x component and the y component using trigonometry, right?
You might be missing t for the vy for the displacement.
You're very correct. Thank you. Yep. Yeah. T there. Okay. All right. So that's projectile motion. Another thing we're going to talk about is relative motion, right? So relative motion is, again, I've been talking about that example of the planes. One's traveling due north, one's traveling due east. There's essentially a way to connect. Not connect. Okay. Basically, you know what? It helps when we see the example. So I'll just leave this here for now, and then we'll come back to it. For curvilinear motion, right? Okay. Basically, we have our curve, and then we have our particle traveling along this curve. Its acceleration component, right? It might look something like this. The acceleration could actually be diagonal, but we have a formula that we can use to calculate its tangential acceleration and its normal acceleration, and we can use like Pythagoras theorem to find the magnitude of that diagonal one, right? So these two components, these are its formulas. So the normal one corresponds to that formula. The tangential one corresponds to that formula. So I've done it in the, I guess like calculus expression, but essentially it's just, if you want to do it in a linear way, it's just that, right? Change in V is over change in T, right? Angular velocity and arc length. I mean, we won't actually see it in this workshop. Helps to come back to it because these will be important formulas for when we do rigid body, rigid body kinematics, right? Okay. Does anyone have any questions? So I've just done an overview of what we're going to see in this next few questions, right? Okay. So this first one is a projectile motion question, right? Because we've got a projectile being thrown. So of course we're gonna, as our coordinate system is y is positive direction there, x is a positive direction going to the right. So the boy is throwing a ball from point A and is trying to hit the top of the roof, right? It has an initial speed, the ball has an initial speed of VA, which is its diagonal, the diagonal vector for velocity here. Right, so we can split that up into its horizontal component and vertical component, right? Which we'll do first. Determine this angle, right? So this is actually a difficult question. I couldn't find like a simple question, to be honest. Like all the projectile motion questions, at least that I've seen in like the civil school and the mech school from like the workshops, they've been pretty hard. I don't know. I think if you look through like high school textbooks and stuff, you'll be able to find like simpler projectile motion questions to start with, if you like. But yeah, so as soon as you have to find this angle, it becomes a little bit difficult, in my opinion, right? So yeah, it tells you to determine that angle and this max height of C. Sorry. No, my bad. So C is known, like the position of C is 8 meters, right? Because it's sitting at the tip of the house. Find the distance D where the boy should stand to make the throw. So basically we have two major unknowns, right, which is that throw angle and that distance away from the house that the boy is located, right? So essentially we're gonna have to do simultaneous equations to solve this, right? So this is like the redrawn diagram. I've called this y final, right? So y final is 8 meters from the ground, so that's the tip of the house. And I've called this yo. Yo is the starting height. Right, the datum that I've chosen, which is just our reference point, is the ground. Right. Okay, so we need to find an expression for we need to find an expression for theta A, right? So at time equals 0, we can always split our diagonal into its components first. So the diagonal velocity vector. which I'm going to call Vx, right? This is 15. It's 15 cosine, our unknown, right? Right, and we also know that our acceleration in the y direction is negative 9.81 meters per second squared. Right, so that's great. That's our, I mean, I can also write this if I want, which is the acceleration in the x direction is 0, but you don't have to write that because it's implied as well, right? Okay, so we need to create this function for our, sorry, we're going to do our vertical motion first, right? Vertical velocity. Right, so the way we do, sorry. The way we do that, Vt is equal to 15 sine theta a, right, which is our initial portion, right, plus the acceleration, sorry, minus 9.81 basically. That's the acceleration in the y direction multiplied by t, right, like that. And at the apex of the throw, you know, let's call it Tc. It's Tc, by the way, sorry, because it's the time it takes to reach that point in the house. We know is 0 meters per second, right? So that's the apex of the throw. So that's kind of like our, actually, yeah. Okay. Basically, this will give us, how am I going to say this? This is like an initial, give me 1 second. We're going to sub in v is equal to 0, and then we can find what Tc is, right? We can find the time of when it reaches the top of the house. So I'm just not good at explaining algebra. Like, okay. So basically, we're copying this part over, right? I'll just show it to you visually. Tc, that's what we're solving for, yeah? And that information plugs in here. You know what I mean? Yeah, okay, good. So when we rearrange for Tc, 15 sine theta a is equal to 9.81, oh sorry, over 9.81. This will be our first equation for our simultaneous equation. Right? Okay. Here's basically what I've written in the formula sheet from earlier, if you want to just plug it into here. Yeah. So this is the displacement in the y direction. It's the y direction. That's 15 sine theta a multiplied by t minus 9.81 over 2 t squared. Yep, so Brad, you were right. That's where the t from earlier was. Okay, so when you plug in Tc, right, we know that the displacement is 7 meters. So it's 7 meters above where it started, essentially, right? It gained the height of 7 meters. You know what I mean? Like, yeah. So 7 is, we're doing the same thing where we're plugging in this this number, right? So I'm just gonna copy this over. Here's Tc, here's Tc squared, right? And you can imagine here's our second expression for t. So basically what we're going to do, we're going to get that box, right? We're going to use the substitution method, plug that right in, like that. Should give us this. Yeah. We're going to, I think I just, how many steps did I skip? Okay, I'll write the intermediate calc, but yeah. Oh, okay, makes sense. We have one sign here, one sign here. It becomes sine squared, right? Which is what results in that part. 15 times 15 is 225, right? Divided by 9.81. That's what that all is, right? And then minus 4.905 is 9.81 over 2. 15 squared is 225. 9.81 squared is at the bottom of the fraction there, right? And we still have our sine component that's like that, right? Okay, so basically we rearrange for sine squared beta a, right? Which equals that. You can square root both sides. And we basically do sine to the -1 of that, which gives us 51.38 degrees, right? So again, this is not representative of a typical projectile motion question. I just can't find a good one. This is a difficult one, right? Okay, now we can find the horizontal distance d. Horizontal distance d, we can plug back in that equation, right, which we've called 1. Like that. Plug this in, 51.38 degrees, right? Gives us 1.195 seconds, yeah? So that's the time it takes from when he starts to throw to when it reaches the apex, which is also the top of the house, right? Okay, what have I done? I need some more space, so I'm gonna make this smaller. Yeah, sweet. Okay, so that's vertical motion. Vertical motion is the hard part. Horizontal motion is pretty trivial. Basically, the velocity in the x direction is constant, and we remember it's just equal to that initial component the entire time, right? Which now we know is, it was a function of some unknown angle, and since we know the angle now, we can plug it in, get 9.363 meters per second, right? And then Sx is just equal to that initial x velocity multiplied by time, right? So, yeah. Sx, oh yeah, basically, we care about this distance d, right? And so we're trying to find this first, right? So this is Sx at time is equal to time it reaches, like it takes to reach C, right? So Sx, when you plug in, time is equal to Tc, which is equal to 1.195 seconds, right? Sorry. We have 9.363 multiplied by that time, right? And we get that that is equal to 11.19 meters. And d, that distance, was simply that number, right? So Sx at t is equal to 1.195 seconds minus 4 meters, which gives us 7.19 meters. So it's minus 4 meters because the house, from the center of the house to the edge of the house, is 4 meters, right? Okay. Any questions with that? Okay. It's annoying, but each of the steps hopefully makes sense. Like, it's just a long question. Yeah. Okay. Next we'll do circular motion, and then the last one we'll do will be relative motion, right? So, curvilinear motion, I should say. So, okay, basically the car travels along a curve. The radius is 300 meters, right? If the speed is uniformly increasing from 15 to 27 meters per second in 3 seconds, right? Determine the magnitude of its acceleration at the instant, the magnitude of its acceleration at the instant its speed is 20 meters per second, right? That's what we're looking at here, right? Okay, so we know that that radius is 300 meters. That'll be important for when we plug in our formula for the normal acceleration, normal component of acceleration, right? Okay, and the initial velocity, we were told here, was 15 meters per second, and it increases to 27 meters per second, right? Okay, so now we have all the pieces we need. So yeah, we literally just plug in basically this V, which we plug in, right? Okay, how do I say this? So we're basically increasing from 15 meters per second up to 27 meters per second, right? The value we plug in for the value we plug in for V is going to be 20 because that's the snapshot in time we care about, right? It's at this unknown time at the moment, right? So we're going to plug in 20 squared over this radius, right? And this will be our normal acceleration, which is also called our centripetal acceleration, right?
Yeah.
That's 1.33 meters per second squared. And then for our tangential component, remember, if we're talking about a linear acceleration, right? It's change in v over change in t. We need 2 points, right, when we do delta v. So we're going to take these 2 points here, right? Because we don't know this, right? So this would be an unknown amount of time. I mean, we can calculate it, but it's annoying. But we do know that delta t here is 3 seconds. Exclamation mark. So we're going to take those 2 values, right? Because that will give us the correct slope, right? So it's going to be 27 minus 15 over 3 seconds, right? Tangential acceleration. Yeah, anyway, that's the, tangential acceleration is basically this component, and then normal acceleration is how much it wants to accelerate towards the middle of the circle, right? And then the overall magnitude of acceleration is going to be this diagonal kind of vector, like that, right? Everyone following? Maybe, you know? Okay. So what we're going to do is calculate exactly that, which is that diagonal component, right? Oh, you know what? I might. Did I ask for the angle? It didn't actually ask for the angle, but for some reason I've decided to do the angle. Okay. I'll draw it out. If we're looking at the acceleration components, AT goes this way, AN goes towards the middle of the circle, right? And then what we're finding, which is A, right, the net acceleration, it's going to be diagonal, and we'll take this as that angle, right? So this is angle away from the tangent. So that's going to be 1.33 and 4, and we're going to utilize Pythagoras and vectors and stuff like that to find that magnitude. So that's the answer. But for some reason, I've also decided to include the angle. I don't know. So yeah, if you're curious what that angle is, it's that. So that angle is that. Yep. Okay. Everyone okay with that kind of concept? Yep. I feel like half of this course is maths. Oh, sorry, half of the dynamics portion of this course is maths. The other half is understanding kind of like the hierarchy of, particles, rigid bodies, kinematics, kinetics. It helps you understand what the question's asking for, how to solve it. So if you can kind of look at a question and understand the rough steps, that's the first step basically when you're solving dynamics questions. And then the next step is looking through a formula sheet to find which formula is most appropriate essentially. So because it's a very broad part of the course, right, there's gonna be a lot of formulas and you're gonna get overwhelmed. You're not gonna know which ones to use unless you can kind of at least categorize what the questions are. That's why I'm going through so much effort to explain, okay, this is a curvilinear question and what it looks like. Okay, this is a, relative motion question, right? Because it's going to help you a lot in the midterm. And then, starting from next week as well, you're going to have to consider, okay, when do I have to use the work energy methods? When am I going to have to use the impulse momentum methods? This is a lot, but yeah, I'm going to try to cover all the bases basically. And then hopefully you shouldn't be surprised when you see, it could be any number of questions, any number of types of questions in your paper. So hopefully, yeah, you're not overwhelmed when you look at your paper basically. I remember the first time I taught 1300, it was in, term 2, this time last year. And I feel like I didn't explain the dynamics very well. And people were literally asking me, are we looking at it top down? Are we looking at it side on? I'm like, fuck, okay, I didn't do my job properly basically. Because the first thing you should do is be able to identify what coordinates we're talking about for are we talking about the wider dimension where it has gravity involved? Are we talking about, billiard balls where it's top down? A lot of these things are just implied, you know what I mean? Yeah, anyway. Sorry, I just started ranting for no reason. Okay, so we have two cars here. Car A is this one on the left. It travels due east at a constant speed of 36 kilometers per hour. Car B starts from rest, so that's car B there, and accelerates south at 1.2 meters per second squared. What is the relative motion, velocity and acceleration of car B with respect to A 5 seconds after car B starts accelerating? Okay, so just looking at these two and these numbers that you can see, what's the first thing you should do? Very good. You should definitely convert away from kilometers per hour into SI units. So in the dynamics portion of the course, we're going to be using, meters, seconds, newtons, whatever. SI units, right? in statics we used like kilonewtons and meters, and you probably didn't see kPa, but this was for beams. And then in your space gas modeling assignment, you probably saw like MPa, millimeters, Newton millimeters, all that stuff, right? But yeah, we just deal with SI units for dynamics, right? There's one question I saw and it like annoyed me. It was from a textbook and they used like pound inches, and I'm not dealing with that shit. I skipped the question. Anyway. Yeah, so convert VA into SI units basically, right? So the way you can do this, I'll do it once and then we won't have to see this conversion again. Basically, you want to think about it like, okay, 1 meter per second is, sorry. Yeah, I'll just show you the conversion. It's basically this, these units cancel out. So you divide it by 3.6, right? You either times by 3.6 or divide by 3.6 when you're doing this conversion, and you have to think about it logically, right? So if we're going like, say you're driving in a car, you're going 40 kilometers an hour in a school zone, right? If you times it by 3.6 to get meters per second, you're gonna be going like over 100 meters per second, you know what I mean, in a school zone. That's just not how it works. So in that case, you think about it logically, how the numbers work, and you just divide it by 3.6, you know what I mean? And then vice versa for the other conversion. Okay, so I'm going to start using I, J, and K. I think I might have briefly gone over this in week 1's workshop, but these are the unit vectors, right? So, here I've drawn them. So in the wider, did I do it the wrong way? That looks like the wrong way. Yeah, fuck, okay, my bad. So I is the one that corresponds to the X direction, right? J is the one that corresponds in the Y direction. And that's what we're going to roll with. So I want to express it in terms of, of unit vectors, right? So I'm going to leave it like that. Okay, step 2, we're going to still use that idea of function is equal to the initial value and then the change over time, essentially, right? So car B, right? Car B is this one. It starts from rest, right? We're told that car B starts from rest. So this is going to start at 0, and its acceleration over time was negative 1.2 J. So this is relevant because J is positive that way, and it's moving downwards, right? So it's going to be a negative J, that, right? So VB is equal to negative 1.2 T J. Right, so that's its function. So we've got an expression for A and we have an expression for B's velocity as well now, right? So we want to find the relative velocity, right? And yeah, not only that, we want to find the relative acceleration, and we want to find what the values are at time is equal to 5 seconds, right? So 5 seconds after the car starts moving, right? So basically, we have this, let me just copy this over. Yeah, we sub in time is equal to 5 seconds. And then we get negative 6J, right? So this is the velocity at 5 seconds for B. And then for A, A is just this. A is always constant. A is always constant, so it was 10 going to the right. Let me erase this. Okay, here's the way you think about it, right? you draw VA and you draw VB as a vector diagram, and they're both originating from the same point, right? So VB is this one, and it's going down, right? And then VA is going to the right, and I like to draw them to scale relatively, like that, yep. And then basically, if we want an expression of, what did it say? Velocity of B relative to A, right? That's VB slash A. We have to do this, right? This is the velocity of B relative to A. It's basically, imagine you're the car that's driving on the path of A. The velocity of B looks like it's going down, right? And it's looking like it's going to the left. Do you know what I mean? That's the way that you think about it. So then at that point, you know, yeah, that's where B is, right? Okay, basically, there's a formula for VBA, right? So VBA, sorry, velocity of B relative to A. Here's how I think about it, right? Tip to tail arrows, right? Like that, right? So velocity of B, which is this arrow on the left, is equal to if you travel the distance of VA and you add on the distance of VBA, right? Yeah? Okay, now we're going to rearrange for VBA. And it's going to be VB minus VA. So that's another expression, right? So basically, we're going to sub in this value for VB. And we're going to sub in this value for VA. So the reason why I've done it in terms of unit vectors is because they're not going in the same dimension, right? You can't subtract the numbers directly. You have to subtract them as if they're vectors. Right, so you have a vector in the j direction, you have a vector in the I direction. So now we have an accurate expression for this, right? So VBA is equal to negative 10I minus 6j. And that's in meters per second. Okay, that's our answer. Right, that. Okay. And the acceleration of, okay. If we look at our question again, right? A is a car that's traveling at a constant speed, so it's not accelerating, right? B is a car that's accelerating, but starts off at, 0 speed or whatever, but it still has that constant acceleration, right? So how these arrows look in terms of relative acceleration, it's like this. Okay, I might. Oh, fuck, sure. This is V, like. Okay, these arrows are inaccurate, right? But what I'm trying to tell you is because this is 0, right? This, it's not accelerating. Then the tip to tail is like that, right? So these are equal, right? So acceleration of B is equal to acceleration of A plus acceleration of B relative to A, but acceleration of A is 0. So acceleration of B relative to A is simply going to be just this one, right? Which is that. So it looks like that. Oops. Okay. Does anyone have any questions? Okay, firstly, let's talk about why we need them. So I've heard people say like curvilinear motion and circular motion like interchangeably, which for these formulas that you see in like using NT coordinates, they are essentially the same thing, because curvilinear motion, circular motion is essentially a subset of curvilinear motion, right? It's where, you know, you have an origin and then it's like a set radius essentially about that origin, and that's like how your particle is moving through space, right? I'll let you guys copy this down, but this isn't the part I'm getting to. You know, this isn't like the critical part, right? But you know, you should get. This shouldn't be a surprise. Like, these are the the circular motion formulas, which I've said last 2 workshops ago. But think about it like this: if there's a satellite dish that's like situated at origin O here, and then it's tracing a rocket that's following this path here, right? The radius is going to change, and the angle is going to change. And same for the robotic arm. You know, this is following a sinusoidal radius, you know, function essentially, right? For the so these are instances where curvilinear motion isn't necessarily equal to circular motion, right? Okay, so let's explain it a little bit more. So, firstly, what are polar coordinates, right? So, polar coordinates are these ones here. Just like with XY coordinates, just like with NT coordinates, right? Normal tangential. They're at 90 degrees from each other, like your grid system. But these can change over time, right? So as this robotic arm, for example, rotates like here, your radial direction might look like this. You know, the grid is basically just shifted, right, in rotation. But for these questions, generally they will give you a snapshot in time at a set angle, and then your coordinate system is not going to change. I guess like within the question, if that makes sense, right? Okay. So, but focus on this if you're confused about what the rotational direction is. The radial direction is like parallel to this is a robotic arm, for example, or like parallel system. Right. So the radial direction is just like in line with that, right? And then the rotational, basically theta, right? Theta is perpendicular to that. That's how it works, right? Okay, so these are the formulas which describe the velocity in the radial direction, the velocity in the, I don't know the word for it. It's like in the theta direction, basically, right? The acceleration in the radial direction, and then the acceleration in the theta direction. So if you've never seen this dotted notation before, the dot means the derivative of, or like, so for example, R dot is the change in R over time, right? Make sure you convert your angle, or change in angle rather, for these formulas, because you see with these formulas none of them will directly plug in theta. Convert theta dot to radians per second, and convert theta dot dot to radians per second squared. So that's change in the angle, right? I guess it's called angle. It's change in the angle, and that's the change in the change in the angle, right? Which is like the angular acceleration. Yep. So R is radius. Theta is the angle. Yeah, sorry. I think I did a pretty bad job explaining before. R dot is your change in radius over time, right? Theta dot is change in angle over time. I guess you can call this the I don't know, I'll just keep it to that, you know. Yeah. Theta dot dot, change in, right? And oops. Basically, okay, let's talk about this hydraulic arm while you guys are copying that down. This hydraulic arm, you know, we'll talk about rigid bodies in week 10, but the entire object's a rigid body, but we're focusing on the particle motion of that pin at the end, right? And since this is a single point in space, it's a particle, right? That's what these formulas are describing. It's describing the motion of how that, let's call this point A, how point A moves over time, right? So the velocity, you know, like the velocity of this, of point A, right? It might look something like this, right? V. But there's two components to it. There's VR, which is the velocity in the radial direction, and then there's V theta. You know what I mean? So these are components. Just like how we had force components, you know, like the force in the x direction, force in the y direction, we're splitting up the velocity into the radial direction and the angular direction, right? Similar with acceleration, essentially. We're finding it'll probably accelerate, like based on what I've drawn here, this one will probably accelerate like this way. It will be a negative number in terms of like AR, and then this one will be like A theta, right? But it's all relative to that coordinate system which we've established here, and the net acceleration will probably be like this way. Yeah, we're gonna go through a worked example, yeah. Okay, another thing, just because, you know, because we have components, right? Just like how we had x components, y components, now we have radial components and theta components, right? To find that diagonal, the magnitude of that diagonal here and here, we have to do Pythagoras theorem, right? So we take the square root of those two components squared, sum together. Here, you don't actually need these formulas. It's basic. I mean, I guess you can write it if you want to do it all in one step. But I generally calculate these first in one line, like this, and this one's like this, and then get it as a number and then plug it in anyway. But yeah, it's just Pythagoras theorem for both of those components. You can copy this down if you like. I guess you can call this the particle's net velocity and net acceleration, right? So, yeah. Again, that particle we're talking about, for that instance I was drawing above, is just that end point of the hydraulic arm or piston or whatever, right? Just tracking that particle through space. Is everyone okay with that? There is a specific case of circular motion within curvilinear motion with the coordinate system. I don't want you to focus on this too much. It's basically where r is constant, right? And you can imagine that just means that the change in radius is 0, and then therefore the change in radius is 0. That's how these formulas. These are the same formulas as before, but I've just turned the change in radius and change in radius to 0. That's a specific case of curvilinear motion for circular motion, right? I'll let you guys copy this down if you want, but like, this isn't the case that we're focusing on today, right? You know what I mean? So let's not waste any time. Okay, so here's a question. A hydraulic cylinder rotates about point O. The exposed length of the piston rod L, right? So you gotta use your imagination a little bit here. Here's the exposed piston length. Here's the rest of the hydraulic arm with a set length of 300 mil. right, rotates at a rate of change in angle is 80 degrees per second, and L is decreasing at a constant rate of 100 mils per second, right? Calculate the velocity at point A, so again, the end of that hydraulic arm, and the acceleration of that point, right? When L is 100, right? Yep. So I'll just scroll down slightly, right? So the first step is we should list out L. Oh, sorry. We should express everything in terms of R. So R and theta. So question, is L the same as R? No. Why is that? L is just this part, right?
Yeah.
R is the entire thing. R is the radius of the whole thing, right? So L is 100, but R is going to be 400 because R is 300 plus L, right? We want everything in terms of R, right? The formulas work in terms of R. L dot rather. L is decreasing at a constant rate of 100 millimeters per second, right? That means that this is shrinking 100 mils per second. But is L dot the same as R dot? You sure?
I guess because it's like fixed 300.
The length is different, for sure. Okay.
The change in length.
The change in length is the same, right? So if I have like a piece of rope, a very long piece of rope, and I'm burning it at a rate of 100 mils per second, doesn't matter how long that rope is, it's burning at the same rate, right?
Right. Yeah.
Yeah. So that's the same as R dot, right? L dot dot is 0, right? It says constant rate, so it's shrinking this robotic arm at a constant rate. Yep.
Where did you get the negative 100 millimeter per second?
Oh, sorry. L is decreasing at a constant rate of 100 mils per second. Yeah, yeah. So that's that whole like burning rope analogy, right? And it's constant rate, yeah? So that means that that shrinking doesn't accelerate over time. Your rope isn't speeding up as it's burning, right? So the L dot dot is 0. And so is R dot dot. Yeah? Okay. Theta, right? Theta, it doesn't say in the question, but I've drawn it here. Theta is at angle 0. We've considered, that flat as 0 degrees, sure. It actually doesn't matter. It doesn't, like, the formulas won't change if this, oh, sorry. I shouldn't say it doesn't matter. The length, okay. Basically, sorry. These formulas aren't dependent on theta. They're dependent on theta dot. So even if you don't know what theta is, if I didn't give you 0 degrees, but you were given that the length was 100 mil, then you can still solve the question. Do you know what I mean? So you don't need to know that that's theta dot. Oh, sorry, that theta is equal to 0, right? So theta dot though, all right, let's read the question, yeah? It rotates at a speed of change in angle of 80 degrees per second. It's 80 degrees per second, right? Let's convert it to radians. So let me explain why now you have to convert it to radians. Let's equal to this though. So if you look at these formulas on the right, it's the same as the ones from above, right? Let's look at this formula. R multiplied by theta dot. You can't multiply meters by degrees directly. Normally we do, you know how we do like sine whatever angle? The sine function cancels out those units of degrees, but radians are essentially unitless, right? So the only way that you can multiply a radian without the sine part, an angle without the sine part, is through radians, right? When you can multiply meters by radians, which are unitless, and still get, yeah, anyway. So anyway, my point is convert to radians. Yeah, that's a long way of saying that. Okay, it's rotating at a constant rate. So, yeah, theta dot dot is 0. Yeah. Okay, next we have to apply these formulae, right? So we have all these listed now. So now it's just a matter of punching them in. So V R is R dot, right? And we've established that R dot is negative 100 mil, right? Per second, sorry. And then V theta, which is the velocity in that theta direction, is R theta dot, based on the formula. And the radius was 400 at that instance in time that we're analyzing, and the rotation per second is this in radians, right? Yeah. AR is the acceleration in the radial direction, right? This was 0, and then the other two components are non-zero, so we'll write them out. Radius was 400, and change in angle, again, it's that in radians, right? That in radians per second, I should say. Okay, and then this next one, this is the next formula. This component is 0, so it cancels out the whole thing. And then, so this part, I'll write it out, is 2 multiplied by the change in radius is negative 100 mils per second. And this one is, yeah, 1.396. All right, let's equate these. So these are this and like this. Okay. Oh, one quick comment on your test. I noticed as I was looking through the marking, I feel like they do ping off like a mark if you don't include units sometimes. So just be careful with your units. Like, it's better safe than sorry. So write out all the units in all your steps and all that crap, I guess. Okay, do you see how we've just applied all the formulas, right? But do you see how the top two are highlighted in orange and the bottom two are in purple? So these will make up our Pythagoras components, right? Right. Yeah, makes sense. So you guys copy that. That's the answer they were looking for the velocity of the particle, and this is the answer they were looking for the acceleration. Right. Yep. All right, I'm going to leave it on that slide.